We're going to do some calculations related to calorimetry. One of the common types of experiments that students do is placing a hot piece of metal into cool water and measuring the heat transferred from the hot metal to the cool water. In this example, the metal would be the system. It's the thing that we're interested in. The water would be the surroundings. Remember, the system and the surroundings have the same magnitude but opposite signs. The Q of the metal equals the negative of the Q of the water. Again, it's not saying that the metal is necessarily positive and that the water is necessarily negative. It's just saying that they have opposite signs. In this case, the Q of the metal is a negative number because heat is going out of the metal. For the water, Q is going to be a positive number because heat is being added to the water, is being gained by the water. Let's look at this example for calculating the specific heat of a metal using calorimetry. We're told that a 59.7 grams piece of metal was submerged in boiling water and then transferred to 60 milliliters of water that had an initial temperature of 22 degrees Celsius. The final equilibrium temperature of both the water and the metal is 28.5 degrees Celsius. We're also given the specific heat of water in the problem. You do not need to memorize that. We're trying to find the specific heat of the metal, then we can look up the value in a table and make a guess about the identity of the metal. As we do this type of problem, it's going to be really important to identify our variables correctly. We're going to need to identify our variables for both the system and the surroundings. In this case, the metal and the water. We will use the Q equals mc delta T equation twice, once for the water and once for the metal. For the metal, we know several pieces of information. We know the mass of the metal is 59.7 grams. The specific heat of the metal, C, is unknown. That's what we're trying to solve for in this problem. The initial temperature of the metal is 100 degrees Celsius. We know its initial temperature is 100 because it said the metal was submerged in boiling water, and we assumed that it was allowed to equilibrate and have that same temperature as the boiling water. The boiling point of water is another Celsius temperature you should have memorized from Chapter 1. The T final of the metal is 28.5 degrees Celsius. Again, that's the equilibrium temperature, when the heat transfer is done and both the metal and water have the same thermal energy. For the water, we know the mass of the water is 60 grams. How do we know that? We're told that the volume of water is 60 milliliters, and water has a density of 1 gram per milliliter. Anytime we're talking about water specifically, not any other substance, if we're given the milliliters, then we can just change those milliliters to grams because of the one-to-one conversion. In this problem, the mass of the water is 60 grams. The specific heat of the water is given to us in the problem, and that's 4.184. The initial temperature of the water is 22, and the final temperature is, again, 28.5. Again, that 28.5 is the final temperature of both the water and the metal. Our first step is solving for the Q of the water. That is, the amount of heat that's absorbed or released by the water. In this case, it's absorbed by the water, because the metal is hotter than the water. If the metal were colder than the water, heat would be released by the water and absorbed by the metal. In our first step, we're plugging all of the variables related to the water into the Q equals mc delta T equation. We can't mix and match water and metal in the same equation. One time we do the equation with the water, a different time we'll do the equation with the metal. Right now we are doing the equation with the water. We plug in the mass of the water, which is 60 grams. We plug in the specific heat of the water, which is 4.184. And we plug in our temperatures for the water. Again, delta T is final minus initial. So we do 28.5 minus 22. We come out with 1,631.76 joules as the Q of the water. Notice this is a positive number which indicates that the water is absorbing heat, which makes sense since the heat is going from the metal into the water. In our second step, we're going to find the Q of the metal based on the Q of the water we just solved for. Remember, the metal and the water are going to have the same magnitude for their Q, but opposite signs. We're just going to slap a minus sign on that 1,631.76 joules, and that's going to be the Q for the metal. In our third step, we're going to plug that Q of the metal that we just solved for into our Q equals mc delta T equation. But this time our unknown variable is the specific heat, C. Again, as we use this equation, all of our variables need to be related to the same thing. In this case, they all need to be related to the metal. We plug in Q of the metal, which is negative 1,631.76 joules. We plug in mass of the metal, which is 59.7 grams. We plug in the two temperatures, final minus initial, so 28.5 minus 100. Notice that gives us a negative value for delta T, a negative 71.5. But Q of the metal is also a negative number. Those negative signs cancel out and give us a positive value for C. Our answer is positive 0.382 joules per gram Celsius. We can look it up in a table of specific heats and find that it's likely to be copper. A 38.6 gram piece of metal at 75.4 degrees Celsius is dropped into 98.6 grams of water, originally at 29.5 degrees Celsius. The final temperature of both metal and water is 37.8 degrees Celsius. What is the specific heat, C, of the metal? The specific heat of water is 4.184 joules per gram Celsius. Is it A, 3,520 joules per gram Celsius, B, 91.1 joules per gram Celsius, C, 2.4 joules per gram Celsius, or D, 731.6 joules per gram Celsius? The correct answer is C, 2.4 joules per gram Celsius. As you solve this problem, follow the same three steps. First, solve for the Q of the water. Second, just change the sign on that to solve for the Q of the metal. Third, plug in that Q of the metal into your equation for everything related to the metal, and solve for C of the metal, that is, the specific heat of the metal.